Hey, welcome back. This is the final exam review for Calc 2. The first section we worked with was differential equations, and if you keep taking math, you'll see that again, so I'm not going to beat it to death. All I want to do is kind of look at 6.2 and 6.3. So basically the way it'll go, if you don't see it in my video, I'm not going to put it on the test. I'm going to give you question pools, like for instance 6.2, you can expect maybe to see questions similar to 29 to 35 odd, and these were basically fill in the chart problems for exponential growth. So 6.2, we give you kind of the most fundamental differential equation in the Mathiverse. And that is that the change in the rate of the growth of the population is proportional to the population at any given time, t. Okay, and if you solve this differential equation, you end up with the formula that you're generally given. So if you solve this by separating and that sort of stuff, you end up with our formula P equals CE to the KT. Okay, so this is the formula you use, and in this problem we'll see that. So this is the most fundamental, easiest formula, but also very simplistic. In particular, you're never going to have a population like of people that grows exponentially without any sort of a limit, right? And we had also that section on the logistic equation, which is more realistic because then it has a limit to the amount of growth you can have. But anyways, problems in 6.2, sort of the table problems like 31. Okay, so we had 226, I think that's radon. And then they give you some information you have to fill in the chart. So it's basically a pre-calc problem. But now we kind of know where we get that nice exponential growth equation. Okay, so 1 half-life initial amount, and t, at that time t is 1,000, and then again t is 10,000, and they tell you the half-life is 1599, and then you get 0.1 grams after that 10,000 years. Okay, so you can use this formula. You don't have to derive it. The P equals CE to the KT. Population is equal to the initial amount times E to the KT. Okay, so you kind of want to chase down the unknown variables, and the first thing you can chase down is the K value. So the half-life says in 1599 years, half the initial amount will be gone. So 1/2 of C will be left over when we plug in 1599 for T, or for K. Yeah, T. No, I want to write K. It's still there. Okay. Solve that for K. Okay. So if you divide both sides by C, you'll have e to the 1599 K equals 1/2, and then you can take logs on both sides. And then on the left, you're using a power rule to bring this down in front. Ln of E is just 1. Remember, log of E, or rather ln of E is equal to log base E of E. And E to what power is equal to E? That's just 1, right? Hey, by the way, what's the ln of 1? It's 0. Okay, anyways, we have this equals ln of 1/2. And then you can divide both sides by 1599. I usually don't go for decimal approximations because then you'll introduce error. So I'm just going to kind of leave this. Okay. Okay, so I use kind of this first information. Now I'm going to use this other guy to hopefully get the initial amount, C. So after 10,000 years, there's 0.1 grams left over. So I plug in 10,000 for t and 0.1 for the p-value, the population, quote unquote. Okay. All right. I don't need the grams. I think I measured better. And then I can solve for c, right? So c will just be 0.1 divided by that big ugly exponential thing. And if you put that in your calculator, make sure you practice putting that in your calculator because that is a big ugly expression. 7.63 grams for the c value. That's the initial amount. Okay. Then we pretty much have all of our information. We could evaluate p at 1,000. Just plug in 1,000 for t into this new formula, 7.63 e to the ln of 1/2 all over 1599 times 1,000. And 4.95 is what I got. Okay, grams. Okay, so basically pre-calc. The calcy part of it doesn't really come into 6.3. And at 6.1 we had sort of algebraic methods for determining solutions to differential equations. So you would have saw Euler's method, just doing basically slope fields as well, and using integration to solve differential equations. At 6.3 we get our first real kind of method for solving differential equations, and it's separation of variables. So we're looking at problems like 3 to the 25. And 6.4, that's where you would have solved the logistic equation. 6.5, that's where we see the integrating factor problems, which you'll hopefully go through all that again once you get to differential equations if you take that class. But anyways, I chose to kind of settle for these types of problems, these separation of variable questions. So let's look at some of those. All right, so you're trying to solve this for some function of x. So you could rewrite it as 2 plus x y prime if you write it in Leibniz form as dy over dx. And basically we want to get all the y stuff on one side, all the x stuff on the other. Okay, so I'm going to divide both sides by y, divide both sides by 2 plus x, multiply both sides by dx. At the end of the day I get dy all over y equals 3 all over 2 plus x dx. Okay. And I always try to keep the constants on the right side. And it's because if I don't do that, I end up having to do funny square root things and things I don't want to do, because that adds complexity and I want to avoid it. Okay. Okay. Once I have it in this form, I can integrate on both sides. On the left, the integral of 1 over y dy is ln of absolute value of y. On the right, if you need a u sub, you can do that, 2 plus x, but it's kind of silly because du will just be dx, right? So this will be the integral of 3 all over u times du, which will be 3 ln of u. And of course, back subbing, you get 2 plus x plus c. Okay. Okay, this is an implicit solution. We want the explicit solution. So we're always hoping to get y equals something, or something that's familiar, like maybe the equation of a circle or an ellipse, something like that, right? So how do I kind of unlock the y? Well, you exponentiate on both sides. So e to all that, e to all that. On the left, the e and the ln cancel, you get absolute value of y. On the right, I'm going to rewrite it as e to the 3 ln absolute value of 2 plus x times e to the c. Okay, you could split that up using the power rules of exponents, the product rule. Basically, if you have e to the x plus y, that's equal to e to the x times e to the y. Okay, I can't simplify this term like I did this term. That won't work. You need to have this 3 out of the way. So to get it out of the way, what you do is use the power rule and put it in as an exponent into the exponent. Okay, so you have the absolute value of y. Let's put the e to the c first, and then you have e to the ln of the absolute value of 2 plus x cubed. Now that they're not, that 3 is there, you can simplify it like we did with the ELNY. Okay, so now you can write absolute value of y equals e to the c, and the e and the ln kind of cancel just like they did kind of up here because they're inverse functions. You end up with the absolute value of 2 plus x cubed. Okay, then we want to get rid of the absolute values, so you can drop that and replace with a plus or minus. And then you can replace this ugly critter with a general constant, which is only dependent on x and y. So basically, we'll say it's dependent on the initial conditions. Okay, and that turns out to be your answer. There's maybe some question as whether or not y equals 0 is a solution, because technically you can't get that thing in the blue box to ever be 0. Yeah, it is a solution. If you plug it into this differential equation back here, it will be a solution. So that question is kind of maybe gets under your skin, but it turns out to not be kind of an issue. Okay, so anyways, let's look at another one. Right. So this one, 23, we want a particular solution. So to do that, we need an initial condition. So we have u times v sine of v squared, and then you have u of 0 equals e squared. So you know it's sine of v squared and not sine of v squared, because if it was this guy, they would have written it sine squared v. Okay. I think a lot of people kind of ask me that question, but they are indicating this. Okay. That's what this means. All right, so anyways, separate. Okay. Get the dv over there. Integrate. On the right, I need a u sub this time. Let's do a z sub, right? Oops, 2v, not 2z. Okay. So I got the integral of v sine of z times dz over 2v, which will be, you can factor out 1/2. The v's will cancel, and you just have a sine z dz. So I have 1/2. The integral of sine z is negative cosine of z. Let's back sub. So that's v squared plus c. And then I want to exponentiate both sides. So over here, the ELN will cancel. Absolute value of u is left on the right. I'm going to rewrite it as e to the 1/2, negative 1/2 cosine v squared. I guess you just leave it as plus c if you wanted. I don't see why we really need to get too carried away. Well, no, you can't do that. All right, you're going to have to e to the c it. Then we can drop the absolute value, so you get plus or minus e to the c, and then you're going to just replace that with a constant. Okay, so this thing is your c value then. And then we have our general solution. Okay. For the particular solution, we need to use our initial value, which is given. U of 0 is e squared. Okay. So I plug in e squared for u and plug in 0 for v. Cosine of 0 squared is just 0, so cosine of 0 is 1. 1 times negative 1/2 is negative 1/2. Multiply both sides by e to the 1/2. And you get c equals 2 plus 1/2 is 4/2 plus 1/2, which is 5/2. And then for the particular solution, you're dumping the c value into this formula, and you're getting u equals e to the 5/2 times e to the -1/2 cosine of v squared. Okay? And if you look in the book, they'll have u equals e to the 5/2 minus 1/2 cosine of v squared. Okay? Okay, so chapter 6 stuff, just separation of variables and applying the exponential growth formula. Okay, you need to have that formula memorized to do questions like 31, but also then separation of variables kind of questions. Okay. General solution on the first one and a particular solution on that second one. Okay, so that's good enough for differential equations. You'll see it again if you keep taking math. Definitely important in mathematical modeling. Can't get much anywhere without that these days. Anyways, 7.1 had applications of integration. We skipped a lot of the material. It was on physics and things like that. 7.1 is actually the most important section that you'll use. And the spiel was finding the area between two curves. So maybe you had some curve F and then some curve G, and you wanted to find the area in between the two. How did that work? Well, you find that it's kind of the intersection points, and then you would do the integral from A to B of the top curve minus the bottom curve. Okay, so this would be the top, and this would be the bottom, based off of the running man there. Kind of tell the orientation. They could also put it in the other orientation with respect to y, and so you would end up having maybe something like this, kind of a weird picture, but maybe let's call this one g of y, and then this one h of y, and then your Riemann man is actually going in this direction. Okay, so the top curve would be the h of y, and the bottom curve would be the g of y. Okay, and we'd be going for something like c to the d. Okay, and that would be the integral from c to the d of top minus bottom, but this one would be in terms of y. Okay, okay, that's really the most important stuff in all of chapter 7. I'm not going to do the rotations stuff. I think that's we're not going to use that very much. Even if you take Calc 3, it probably won't come up very much. So anyways, let's take a look at some of these. Number 17, they give you two graphs. They want two functions. They want you to find the area between, or the area that's enclosed by the two functions. So first you have to graph them. Okay, so the first guy is a parabola. Let's find its x-intercepts. Then its vertex, the h-coordinate is at -b all over 2 times a, which is not this thing again. Oh my God. Which is -1, and then the y-coordinate will be 1 minus 2, which is -1. Okay, so -1, -1, and then 0 and -2. So looks like this. And then x plus 2 has a y-intercept at 2, and then it has a positive slope. So it's going to go like this. And the region in between the two. So I need the intersection points, so you got to set the two equal to each other. And that gives you the limit on your integral. So the top curve is g minus the entire bottom curve. Make sure you distribute the negative. And then it's just basically, do you know how to do an integral? Okay. So what do we have? X minus 2x, so 2, minus x squared minus x dx. And you're always putting in the top limit first into the antiderivative, and then subtract the bottom limit into the antiderivative. So putting in the 1 first, minus plug in -2. Okay. 2 minus -4 is 6. -1/3 minus 8/3 is minus 9/3, which is 3. -1/2 plus 4/2 is plus 3/2. So 3 plus 3/2. We'll get 6/2 plus 3/2 is 9/2. Okay. Let's get a little practice in there with integrals. Those things never seem to really go away. Let's look at one that's in the other weird orientation. So this is like 24. F of y is y times 2 minus y. G of y is -y. Okay. So again, I'm going to go after kind of the important parts. So the y-intercepts this time. Okay. And then for the vertices, you have 2y minus y squared. F of y equals that. You could rewrite it -y squared plus 2y. And then instead of having your x coordinate being -b over 2a, the y coordinate of your vertex is -b over 2a. So it's a bit weird. So the k value is actually negative, in this case 2, all over 2 times a, which is -1, which is 1. And then the x coordinate, you plug 1 back into f. Okay? So you get 2 minus 1, which is 2 minus 1, which is also 1. Okay? So I must have screwed it up in my notes. Yeah, I got a mistake in my notes. So the vertex is at 1, 1. Okay, no way to screw that up. Anyways, let's go ahead and take a look at the graph. So I have 0, and then 1, 2. The vertex is at 1, 1. And it's going downwards. So it's -y squared. And then -y, that's just a negative slope going in this orientation. Y-intercept is 0, and then it goes down 1 over 1. So it's going to do one of these jobs. And again, you're looking for the area between these two curves. So this area, I'm going to need the intersection points. So you set the two equations equal to each other. Factor out the y. And it looks like we're integrating from 0 to 3. This time the parabola is on top. And then the equation of line is on the bottom. So minus -y. And then let's get a little practice doing an integral. Clean it up first. What do we have? 2y plus y. That's going to give me 3y's, and then minus y squared. Integrate. And then evaluate the antiderivative. So do the top first, minus the bottom. So 3 times 9 is 27 halves, minus 3 cubed is 27 thirds, minus plug in 0, you get 0 minus 0. Multiply top and bottom of this guy by 3. Multiply top and bottom of this guy by 2. 3 27ths minus 2 27ths gives you 1 27 all over 6. Divide top and bottom by 3, and lo and behold, you get 9 halves again. So those are probably the same objects, just kind of rotated. Okay. Okie dokie. So find the area between two curves. Let's 7.4. I also want to throw in arc length because arc length comes up, it seems like, again and again. We saw it here in 7.4 first. Let's see what kind of question. 7 to 19 odd. Did I give you a question poll for 7.1? No, I didn't. So 7.1, I'm thinking problems like 15 to 27 odd. And then 37 to 41 odd. I'll give you a question poll for these. 6.3, 3 to 25, 6.2, yeah. Okay, so 7.4, you need the arc length formula, you need it memorized. It comes up again and again, so we saw it here first. It has that square root, like a distance formula type feeling. F prime of x squared dx. The other two come then in parametric form and then in the polar form. So there's actually 3 of these arc length formulas floating around in your brain. This is probably the most fundamental one, so I expect you to be able to do these types of problems. Let's look at number 9 from the book. I think there was one like this on the test. So 2/3 x to the 3 halves plus 1 from 0 to 1. Okay, so find the arc length of that curve on the interval from 0 to 1. All right, so to pull it off, you got to define the derivative. So power rule, bring down the 3 halves. 3 halves minus 1 is 1/2. And then the derivative of 1 is 0. So this should just be x to the 1/2. And then the arc length will be the integral from 0 to 1 of the square root of 1 plus x to the 1/2 squared dx. And then that will be the integral from 0 to 1 of the square root of x to the 1/2 squared is just x. So you get 1 plus x dx. Then if you want, you can do a u sub. It's not necessary though, because du is just dx. So there's no constants to speak of. So the integral of the square root of u du, if you wish. Rewrite it so you can do a power rule on it. So you get u the 3 halves times 2/3. Remember to evaluate. Back sub. And then we have 2/3 times 1 plus 1. Plugging the top limit into the antiderivative is 2 to the 3 halves. And then minus 1 plus 0. 1 to any power is just 1. So that would be your final answer. Okay, so good stuff. But that's really the most important stuff in Chapter 7 for us. 8.1 is everything you had learned about integration in Calc 1. I think at the beginning of Calc 2 here. So at the beginning of Calc 2, don't forget, we still kind of have to have formulas memorized for like arctan and arcsecant. So let me just remind you for 1 all over a squared plus u squared du. That's going to be 1 over a tan inverse u all over a plus c. Integral of 1 all over the square root of a squared minus u squared du. It's going to be sine inverse of u all over a plus c. Okay. We actually did that at the beginning of the chapter. We started in 5.7, which I think dealt with logarithmic integrals, or integrals that resulted in logs. Then in 5.8, we did these things, these inverse trig functions. And then in 5.8, I believe we did the hyperbolics. Okay. I probably won't put any hyperbolics on the final, but inverse trig functions are fair game. Of course, along with pretty much any other type of integral you can imagine. So 8.1 explores those integrals and all the little integral tricks like doing long division, completing the square, U subs in general, and 33 we see one of these weird tricks. Either negative x plus 1 dx. So here I'm going to multiply top and bottom by e to the x and see what happens. Because right now you couldn't do a u sub. Before, starting here, you cannot do a u sub because you would be left over. So if you did u is either negative x plus 1, you would get du is negative e to the negative x dx. And that would give you a dx of negative du over e to the x. And there would be no way to, well, I guess you could. You could sub in then for e to the negative x u minus 1, I guess. E to the negative x plus 1. Just make that u. Yeah, well, I guess you could maybe finagle. Yeah, I take it all back. But this is just a clever trick, I guess, you could do. Anyways, let's look at this. So in the numerator, you get 2e to the x. And the denominator, when you distribute, e to the negative x times e to the x. That's rules of exponents. That's just e to the negative x plus x, which is e to the 0, which is 1. Okay. So you would have 1 plus then e to the x times 1, e to the x. And then you could do a u sub for the denominator. So u 1 plus e to the x du is e to the x dx. And then dx is du over e to the x. Okay. So get the integral of 2e to the x all over u times dx, which is du all over e to the x. Then there's a nice cancellation. You can factor out the 2, and you're just getting a log integral. Du over u. That's 2 ln absolute value of u plus c. And then that'll be 2 ln absolute value of 1 plus e to the x plus c. Okay. Just to the side here, Chapter 8, the most of the material on the final exam is from Chapter 8. So probably the most important thing we teach you here will be integration. So the final exam is really heavily weighted towards Chapter 8 problems. Okay. Anyways, let's look at 69. Here I have the integral from 0 to 2 over root 3. So this is a definite integral. 4 plus 9x squared. Okay. Dx. So again, you couldn't, well, this time you definitely couldn't do a u sub for the whole denominator. You would end up with an x floating around, and there wouldn't be too much you could do. It turns out to be an inverse tan formula, right? So if you do a u sub for 3x, du will be 3 dx, because in the denominator you have 4 plus 3x squared. And you want to do a u sub for that 3x. Okay? And then that's going to put it into the form of a tan inverse right here. Okay? Where your a value in this case will be 2. Okay, so anyways, if du is 3 dx, so dx is du over 3. Okay. So I'm going to go ahead and put that in there. You can factor out the 1/3. You're going to be then just using the formula for tan inverse. So our a value in that formula will be 2. There's a 1/3 still floating around, so it's 1 all over a times tan inverse of u all over a, and then we have to remind ourselves to evaluate. Okay, back subbing. So I get 1 over 6 tan inverse of u, which is 3x over 2. And then I'm evaluating from 0 to 2 over root 3. Okay. So we 1/6 tan inverse of 3/2 times 2 over root 3 minus 1/6 tan inverse of 0. That part's 0. This part, though, here, what is that? That's 3 all over root 3. Okay. So what the heck is that? That's the same as, let's rationalize it and see if it looks different. 3 root 3 all over 3. Oh yeah, so that's root 3. So that will be, the reference angle that gives us root 3 will be pi over 3. Okay. So yeah, pi over 3. So this would be 1/6 times pi over 3 minus 1/6 times 0 is just 0. So pi over 18. Okay. 8.2 is on by parts. So the uv minus the integral of v du. Let's look at, so let me get you the poll, question poll, 15 to 33 odd, and then 43 to 51 odd. Can I give you the 8.1? I keep forgetting. I didn't give you the question poll for 8. I keep forgetting I might just write out the question polls here. Okay, so 8.1, questions like 15 to 45 odd, and then 57 to 69 odd. Okay, let me just write out the question polls because I keep forgetting to write them out. So here I go. All right, you may I'll pause my video and I'll write them all out, and then you can just pause your video. Okay. Okay. So there they are. You probably want to pause the video and copy them down. I'm just going to go through and check to make sure I wrote them all out right. So if I didn't list it, I'm not taking any questions from that section. Okay. Okay, so again, it's mainly Chapter 8 that I'm worried about, very little from Chapter 6 or Chapter 9 or Chapter 7, and then some more from Chapter 10. Okay, so hopefully you got that copied. Let's move on now. So I was working with 8.2, and we're doing by parts. So let's look at problem 31. Integral of arc tan of x dx. Okay, so no idea, right? But you can pretend it's a product of two things. 1 times arc tan of x dx. So you could say u, and you have to remember lineate. So log, inverse, trig, algebraic, trig, and then exponential, right? So you go with inverse trig, so this part is considered the inverse trig, arc tan x. And then the dv part will be the 1 dx, everything else. Then to get v, you have to integrate dv, so that will be x. And then for du, you have to differentiate arc tan, so that'll be 1 over 1 plus x squared dx. Okay. If you want to use the tabular method to do these, that's fine. I'm just doing it this way. So it'll be u times v, so x arc tan x minus v, the integral of v du. So that's x over 1 plus x squared dx. Then I need, to get that second integral to work, I need a sub. So u, or let's do a z sub for the denominator, right? Okay, so we'll have x arc tan x minus integral of x over u times, or z, we're doing z subs. X over z times dz over 2x. Nice cancellation with the x's. Factor out 1/2. And I have a basic integral that will give me a natural log. Finally, back sub. Okay, great. Let's see some other versions. So 49 is kind of one of those weird looper ones. So you'll start out and have to do by parts like twice, and then you'll end up back where you started. And then you have to use a variable. Okay. And on top of this one, we're going to have to evaluate when we're done. Okay. So Liet says trig before exponential. So this will be e to the x du, then will be cosine x dx. And then we'll do this times this. So e to the x sine x. And we have to evaluate minus this times this. Integral of that. So e to the x cosine x dx. And it seems like we're no better off, so what we do is apply by parts again to this critter. Okay. So again, trig comes before exponential. There's a negative in there, be careful. You have to remember our derivatives. So we'll have e to the x sine x minus e to the x cosine x minus, which will become plus because of that negative, plus e to the x sine x dx. And we're back sort of to where we started. Okay. So what we're going to do then is to call this integral I, and then this guy over here will also be integral I. And we could rewrite it as I equals e to the x sine x minus e to the x cosine x minus I. And then move the I to the other side. I still have to remind myself to kind of evaluate here eventually. But adding I to both sides gives me two I's. That'll be e to the x sine x minus e to the x cosine x. Don't forget to evaluate. And then finally I is equal to e to the x sine x minus e to the x cosine x over 2. And have to evaluate from 0 to 1. Okay. Okay, so plugging in 1, e to the 1 is just e sine of 1 is whatever sine of 1 minus e sine of 1 all over, well, cosine of 1 on the second guy, all over 2. And then minus, plug 0 in, so e to the 0 is 1, and then sine of 0 would be 0, minus e to the 0 is 1, times cosine of 0 is also 1. 1 times 1 is 1, over 2. So it looks like we're getting e sine 1 minus e cosine 1, there's a common denominator of 2, minus minus becomes plus 1 all over 2. Okay. Okay, so enough of that. Let's go on to 8.3 where we have trigonometric integrals all over the place. So some formulas you may have to remember for these, the reduction formulas. So cosine squared theta is equal to 1 plus cosine 2 theta over 2. Sine squared theta is 1 minus cosine 2 theta over 2. Sometimes those come up. Number 5, I don't think you need it though. This is one of the kind of general issue formulas here. So for these, usually you just kind of push back a factor. So I'll push back a factor of cosine, leaving me with cosine squared of x. And then sine to the 4th x. And then you have 1 factor of cosine x dx. Then you can convert the cosine squared using Pythagorean identities. Sine squared x times sine to the fourth x cosine x dx. Okay? And once you get everything in the front in terms of sine, you just do a u sub for it. So u of sine, and then you'll get a cancellation of the cosine. Derivative of sine is positive cosine. This will be 1 minus u squared times u to the fourth times cosine x times du all over cosine x. It'll be a nice cancellation between the cosines, and you'll just have an easy power rule kind of stuff to do. You have to distribute the u to the fourth still. So you get u to the fourth minus u to the sixth du. And then that'll be u to the fifth over 5 minus u to the 7 over 7 plus c back sub sine to the fifth x over 5 minus sine to the seventh x over 7 plus c. Okay, the next section then, 8.4, was on trigonometric substitutions. There's 3 basic types. If you have something like this, what is it? A squared minus u squared, you're going to use a sine theta. If you have the square root of a squared plus u squared, you're going to a tan theta. And if you have square root of u squared minus a squared, you're going to go to a secant. Okay. All right, let's look at 11. And of course, if I give you a problem and it's like it ends up with like something that I don't expect you to have memorized, like the integral of secant or the integral of cosecant, I will give that to you as a hint on the test. This one doesn't seem to be that bad though. So anyways, x over 2 times the square root plus x squared dx. So it's one of these a tan thetas. A is 2. Okay. So I'll have x equaling 2 tan theta. And for these problems, what I do is kind of get all the ingredients down first, right? So I got dx. I need that. That'll be 2, the derivative tan of secant squared. Then I need to solve for theta. So you solve for theta from this formula. You'll have tan of theta equals x over 2. Then take tan inverse on both sides, and you get theta is tan inverse of x over 2. Okay. And you need that for the end of the problem. So you draw this triangle, and it's going to allow you to get rid of things like cosine of tan inverse of whatever. You know? So here we have theta and tan opposite over adjacent. And then the third side, solving using the Pythagorean Theorem, x squared plus 4. And that should be everything we need. Okay, so you begin by just using the first 2 parts of that box. So for x, it's 2 tan theta over 2. And the square root of 4 plus x squared, so that'll be 4 tan squared theta. And then dx is 2 secant squared theta d theta. Okay, simplify a bit. I can factor out a 2. These 2's will cancel. So I get 2 integral tan theta times, there's a secant squared theta. And that, let's see what this square root thing turns into, right? This will be the square root of, you can factor out 4, you get 1 plus tan squared theta. That'll be the same as the square root of, from the Pythagorean identities, 1 plus tan squared is secant squared. And then taking the square root of that, that's 2 secant theta. So you'll have times tan theta times the secant squared theta from the back, and then there's from the square root 2 secant theta. Okay, d theta. So I can factor out another 2. I get 4 integral theta. I can go secant cubed theta now, d theta. And this is one of the tan secant kind of trig integrals. So you want to push back either the derivative of tan or the derivative of secant, whichever one kind of works. If you push back the derivative of tan, in other words, secant squared, it's not going to pan out because you're not going to be able to get rid of that secant using a Pythagorean identity. So what you have to do instead is push back a tan secant. So you'll end up with secant squared theta times tan theta times secant theta d theta. And then if you do a u sub for secant, du will just be that secant theta tan theta d theta. And things will work out. So d theta is over secant theta tan theta. You get a nice cancellation. I'm going to go u squared now. Then we have the tan theta secant theta times d theta, which is du all over secant theta tan theta. Nice cancel. Boom, boom. And we're left with a nice little integral we could do a power rule on. So 4u cubed over 3. Do we need to evaluate this guy? No. Thank gosh. Let's see. So we got 4/3. Let's back sub. So u is secant of theta cubed. Okay, theta is tan inverse of x over 2. So really this is secant of tan inverse of x over 2. The way you simplify that, though, is to use the triangle. And literally all you need to do is take the secant of this angle and interpret it as the ratio of sides of this right triangle. Okay, so secant is 1 over cosine. So that's going to be hypotenuse over adjacent. So we can rewrite this hypotenuse over adjacent. And then we cube this. And the denominator you'll have 2 cubed, which is 8. So you end up with a 4 all over 8, which is 1/2. And then there's a 3 there, so it's going to end up being 1/6. And then x squared plus 4 to the 3/2. Okay, so trig integrals. 8.5, partial fraction decomposition. So there were 4 types. There's the linear, linear repeated, irreducible quadratic, and irreducible quadratic repeated. Okay, let's get 15. You have the integral of 9 minus x squared all over 7x cubed plus x dx. Okay, so first I want to do the partial fractions on this guy. So I have minus x squared, and I need to factor the denominator, so I can pull out an x. So I get one linear factor, so I use one fraction for that, and then one non-linear fraction, so I use 7x squared plus 1. For the linear factors, you always just use a letter, and then for the quadratics, you're going to have to go something x plus something, right? So bx plus c in this case. Multiply through to get rid of the denominators. So you multiply everything by x times 7x squared plus 1. On the left, you'll just have 9 minus x squared. On the right, when I do this times this, the x will divide out, and you'll have a times 7x squared plus 1. This times this, the 7x squared plus 1 will divide out, and you'll have just bx plus c times x. I'm going to do equating coefficients. So on the left, you can rewrite it as negative x squared plus 0x's plus 9. On the right, I have 7ax squared plus a plus bx squared plus cx. So 7a plus b equals the coefficient of x squared here, which is negative 1. Then c must equal the coefficient of x over here, which is 0. And then a must equal this thing, so a is 9. Okay. So all I have to do is solve for a and plug this guy in over here. So 7 times 9 is 63. Subtract 63. And I have my numbers. Okay, so I could rewrite this integral then as the integral of 9 over x, then minus 64x plus 0. We could just write that as minus 64x all over 7x squared plus 1. And this would be dx. Let me quarantine all of this junk. Okay, the first integral is just a natural log, so 9 ln x, absolute value x. And then minus, for this guy I need a u sub, right? So u as 7x squared plus 1, du 14x, power roll. So dx will be du all over 14x. Okay, so I could factor out 64 if I wish, but let's just leave it as it is right now. 64x over u times dx, which is du all over 14x. And absolute value x minus. You can factor out a 64 over 14, which would be 32 over 7. The x's cancel. And you have an integral of du over u, which is just another natural log. So I'm going to end up with 9 ln absolute value of x minus 32 over 7 ln absolute value of u. Let's see. And then I get back sub for the whatever the heck the u value was. So 9 ln absolute value x minus 32 sevenths ln absolute value of 7x squared plus 1 plus c. That would be your final answer. Okay. Okay, so 8.5 stuff. 5.6 was on limits using L'Hopital's. So let's look at kind of a generic one. As x goes to 0, sine of 5x all over tan of 9x. So you always start by kind of just substituting in where we're headed, so sub 0 in. Sine of 5 times 0 is the same as sine of 0. Sine of 0 is 0. Tan of 9 times 0 is tan of 0. Tan of 0 is also 0. So if you're in the form 0 over 0 or infinity over infinity, then you could use L'Hopital's. Okay. So here I can use L'Hopital's, take the derivative of the top, and you're going to get cosine of 5x times, via the chain rule, 5. Downstairs, you get secant squared of 9x times 9. Cosine of 5 times 0 is the same as cosine of 0. Cosine of 0 is just 1, so I'll have 5 times 1. All over secant squared is basically just a cosine as well. It's 1 over cosine, right? So secant squared of 0 is going to be 1 over 1 squared, which is 1. And that will be times 9. So you basically just get 5 over 9 as your answer. Okay. There are also these other weird ones, like 0 times infinity, or infinity to the 0, and infinity minus infinity. So you should be able to do all those. Let's look at one of these infinity to the 0 types. Those are usually harder. Okay. So in this case, I rewrite it. The way I did it was to rewrite this as an exponential, e to the ln of x to the 1 over x. Then I could use power rule to bring the 1 over x down in front of the ln. Okay. So the limit as x goes to infinity of e to the 1 over x times the ln of x. Then I pass the limit into the exponent. So I have e to the limit as x goes to infinity of 1 over x times the natural log of x. This form and the exponent now is, well, 1 over x goes to 0, and then ln of x goes to negative infinity. So 0 times infinity, you want to rewrite it as a quotient of some sort. And it's kind of already rewritten. Usually you have to do like 1 over x or something. This though is kind of already written. If you just rewrite it as ln of x over x, it's just it'll become infinity over infinity, right? In particular, whoops, I lost my e to all of that. So it'll be e to the this thing, which as I was going on about, that's negative infinity over infinity, which is a form that we could do L'Hopital's on. So the derivative of ln of x is 1 over x. The derivative of x is just 1. Okay, so I have e to the limit as x goes to infinity of 1 over x. And then that's L over infinity, so that's just 0. So you have e to the 0, which is 1. Okay. 8.8 then was on improper integrals, and there's 2 types in there. There's the infinity types. We were seeing the infinity types in the final chapter 9. So let's look at one of the other types, right? So one of the infinite discontinuity types. Okay, so you can see it's an infinite discontinuity because when you kind of plug in the endpoints and see what happens. So you're on this interval from 0 to 5, and you're integrating some function over top of it, and there's actually an asymptote at 0. Okay, so that would be the problem. So you would rewrite it as a limit approaching that asymptote, and in particular you have to approach it kind of from the positive direction. Okay, so you replace the 0 with a b, and then we're integrating 10 over x dx, which is easy enough to do. So limit as b goes to 0 from the right of 10 ln absolute value of x. Okay. Plug in the limits. So first plug in 5. And you get 10 ln 5. And then plug in b. So 10 ln b. And on the natural log function, as you go to 0 from the right, the natural log will go to negative infinity. So what you're ending up with is L minus negative infinity, which will be L plus infinity, which will be infinity. Okay? And that implies divergence. Okay. So improper integral stuff. Then we're fast forwarding to 9.7, where we're doing Maclaurin and Taylor polynomials, so that we could use those then to do approximations for these weird things like the square root of 2. So anyways, the square root of x is what we want to do a Taylor polynomial for. The degree is 2, so you have to go up to x squared, and then the center is 4. So it's Taylor. Okay, so here we go. F of x equals x to the 1/2. Then I need f prime of x, and then f double prime of x. F prime is 1/2 x to the negative 1/2. So I'm just doing power rules. And then negative 1/4 x to the negative 1/2 minus 2/2 is minus 3/2. So I'm going to have to evaluate these at the center. Okay, so 4 to the 1/2 power is 2. Then we have 1/2 times x to the negative 1/2. So that would be 1 all over 4 to the 1/2, which is 1/2 times square root of 4 is 2. So that would be 1/2 times 1/2 is 1/4. And the last guy, negative 1/4 times 1 all over 4 to the 3/2. Okay. What is 4 to the 3/2? Well, that is 4 to the 1/2 cubed, which is 2 cubed, which is 8. Okay, so I have 1/4 times 1/8, which is, and I lost my negative, negative 130 seconds. Okay. Then we just go to our form for P2 of x. That'll be 2, and you want to use the boxes you can. So 2 plus box times x minus 4 plus box times x minus 4 all squared all over 2 factorial. And then plug in the boxes. 2, 1/4, negative 130 seconds. Okay. Okay, 9.8, I like these interval of convergence problems, so expect to see one of those. Let's look at 21. We have the sum of 2n factorial times x over 3 to the n from n equals 0 to infinity. Okay, so to do these interval of convergences, you're using the ratio test. So 2n, we need a sub n plus 1 over a sub n. So 2 times n plus 1. So replacing n's with n plus 1's times x over 3 to the n plus 1. All over a sub n. X over 3 to the n. Usually, it looks weird because usually we're doing reciprocals because we have a complex fraction. Anyways, this will be the limit of 2n plus 2 factorial all over 2n factorial. X over 3 to the n plus 1 over x over 3 to the n. You subtract the exponents and you end up with x over 3 to the n plus 1 minus n, which is just 1. Then we want to simplify the factorials. So let's do the brute force method. 2n plus 2 times 2n plus 2 minus 1, which is 2n plus 1. So you just subtract 1 every time you go down. 2n plus 1 minus 1 is 2n. And then 2n minus 1 all the way down, and it's always 3 times 2 times 1. All over 2n factorial, so that would be 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1, and then of course times x over 3. It looks like some nice cancellations. 2n factorial, 2n factorial. And then the limit of 2n plus 2 times 2n plus 1 times x over 3. You can factor out the x over 3. You need the absolute value still. Comes the limit of 2n plus 2 times 2n plus 1. This part is going to infinity. Right? So this will equal infinity for all values except when x is 0. And when that happens, the only place it converges is at x equals 0. So the interval of convergence would just be the point 0. Okay. So remember, there are questions. There's like 3 versions of these problems. There's the ones where you have this issue, so it's only convergent at the center. There's the ones where it's convergent everywhere. So like e to the x, that power series is convergent everywhere. And then there's the ones where you just have an interval of convergence where you have to check the endpoints. Let's do one more of those, right? So one of these endpoints, these are the hard ones. And I'm more likely to put one of these on the test, but I just wanted to remind you of the other types. Okay, so again, the workhorse is the ratio test. We're going x minus 3 to the n plus 1 minus 1 is n. 3 to the n plus 1 minus 1 is n, times the reciprocal of a sub n. Okay. And then we have the limit of x minus 3 to the n minus n plus 1. Okay, so that would just be x minus 3 over 1 times 3 to the n minus 1 over 3 to the n. you're going to bring the 3 to the n minus 1 down. So you'd have 3 to the n minus n plus 1 when you distribute the negative. In other words, 1 all over 3. So there's no n here, and the limit is n goes to infinity. So this is just the limit of a constant. So you just end up with a constant right back. In other words, x minus 3 all over 3. Okay. Ratio test says it'll converge absolutely for x values such that the r value is in between 1 and negative 1, like this. So we can multiply by 3, negative 3 less than x less than 3. Whoops, x minus 3 in here. Add 3 to all 3 sides, you get 0, less than x, less than 6. Okay, we still need to check those endpoints, though, the places where the r values would be equal to 1. So I need to plug in 0 and plug in 6 into the original series, and then use the basic tests from 9.2 to 9.6 to determine the convergence or divergence. Okay. So let's plug in 0 first. So you're literally just plugging in 0 wherever you see x. So you're going to plug a 0 in there. And your series would end up being 0 minus 3 to the n minus 1. So you just get negative 3 to the n minus 1 all over 3 to the n minus 1. You could rewrite negative 3 to the n minus 1 as negative 1 to the n minus 1 times 3 to the n minus 1. Okay. And then you could simplify by removing these guys, and you get the series of negative 1 to the n minus 1. Here you can either do a geometric series and say the r value is not less than 1, therefore it's divergent, or the nth term test for divergence. So note, I like to use the nth term test. Negative 1 to the n minus 1. That limit does not exist because the even terms go to negative 1 and the odd terms go to positive 1. Okay. Hence, it does not equal 0. So this does not equal 0. And so by the nth term test for divergence, the series diverges. Okay. Let's check out the other endpoint at 3, or rather 6. So plugging that into my series, you go 6 minus 3, so you're plugging in where I plugged in 0 before. I'm plugging in 6. So you'd have 6 minus 3, which is 3. So you'd end up with 3 to the n minus 1. Let's put that in black. All over 3 to the n minus 1, which is just a sum of 1. And then again, you could use the nth term test. So note the limit of 1 equals 1, which does not equal 0. And so by the nth term test, the series diverges. Okay, so expect, expect to build some Taylor or Maclaurin series. Also expect some of these interval of convergence problems, okay, from 9.8. Okay, let's move on to chapter 10. 10.2, we were kind of building parametric functions, graphing them, creating equations for particular geometric objects like lines. So first 41, they want you to take the given parametric equations and convert it into a rectangular equation. Okay? So we have x equals that and y equals k plus b sine theta. I think in the book they want you to identify the form or something. I don't remember. But anyways, to pull this off, we're going to have to kind of eliminate the parameter theta using the Pythagorean identities. So I'm going to solve for cosine theta in the first one. So you have x minus h equals a cosine theta. Divide by a. So you get cosine theta equals x minus h over a. Do the same thing for the other equation. So x k b sine theta. sine theta equals y minus k over b. And then we could use the Pythagorean identity, cosine squared plus sine squared, theta equals 1. Okay. And it's just a matter of substituting in this chair thing I'm sitting on, substituting in those two expressions. So first, put in the x minus h over a. And then the y minus k over b. And what we have, folks, we have an ellipse. Right, this is the standard form for the ellipse. Okay, one thing that's you kind of need to know how to do later on is create parametric equations of lines given 2 points. So again, there's this type of problem in the book. Create the parametric equations for a line going from -3, 1 to 1, 9. And it's basically like you figure out kind of the x slope and then plus the x sort of starting place. So in that case, it will be 1 minus -3. And then you put in -3 plus -3. For the y equation, it's kind of the y slope, 9 minus 1, and then plus your starting place, 1. So you see at 0, when you plug in 0 for t, you'll get -3, 1. So you'll start at -3, 1. Okay, let's simplify it a bit. Okay, so you should be able to, or know how to do that. 10.3, we start introducing calculus to parametric equations, in particular the derivative. You should be able to find derivatives, the second derivatives, find horizontal, vertical tangents, that sort of stuff. Anyways, let's do a derivative type. So this looks like parametric equations for a circle. We want the first derivative, and so the slope of the tangent line at pi over 4, and then the concavity at pi over 4 as well. So to get the slope of the tangent line, you do dy over dx. To get the derivative, it's just the derivative of y, which is 4 cosine theta, all over the derivative of x, which is -4 sine theta. Okay. This will end up being negative cotan theta. And then we want to evaluate the stuff at theta equals pi over 4. Okay, so tan of pi over 4 is 1. Cotan then is just 1 over 1, which is 1, and then it's negative. So it's -1, so we have a negative slope, which makes sense if you think about what a circle looks like. Pi over 4. You would expect the slope to be -1. Okay. Then we need the concavity, so that means do the second derivative. And again, evaluate it at pi over 4. Okay. So to get the second derivative, what you're doing in the numerator is taking the derivative of the first derivative with respect to theta. Okay, so you're doing the derivative of negative cotan theta, which is going to be negative cosecant squared theta. And the denominator, you're just putting the derivative of x again. So you're plugging in -4 sine theta. Okay. So what did I do? I took the derivative of this thing with respect to theta and plopped it right there. And then in the denominator, you're putting the derivative of x with respect to theta again, putting it right there. Okay. And then evaluate it at pi over 4. Okay, 1 over sine is cosecant, so you can simplify this a bit. And the numerator negative is positive, so you're going to have -1 over 4 times cosecant squared theta times 1 over sine, but I'm saying that's another cosecant theta. You have to evaluate pi over 4. So we basically have cosecant cubed. So this would be negative 1/4 cosecant cubed theta at theta equals pi over 4. Cosecant, again, is 1 over sine. Sine of pi over 4 is root 2 over 2, or 1 over root 2. So if you take the reciprocal, you just get root 2. So we're getting negative 1/4 times root 2 cubed. Root 2 cubed is 2 root 2. So you get negative 2 root 2 over 4, which is negative root 2 over 2. So it's concave down. Sad face. Went. All right, next. 10.4. I expect you to be able to graph these polar equations. I think on the test 5 I give you a rose curve, and probably on the final I'll give you some sort of snail. So let's look at 83. R equals 4 times 1 plus cosine theta. Okay. I like to rewrite this as 4 plus 4 cosine theta. Okay, so first you could do a table of values. I like to just draw it in the r theta plane or the theta r plane. The amplitude is whatever's in front of cosine. In this case, it's 4. The period is easy. It's just wedge theta in between 0 and 2 pi. So the period is 2 pi. And then for your tick marks, you just take the period and divide by 4. So 2 pi over 4 is pi over 2. And then this guy has a vertical shift up by 4. That's what this 4 does to it. Okay, so vertical, this 4 up here. Okay. Vertical shift, so it's going up 4. Okay. Okay, so I plot all that stuff in the r theta plane. Ugh, I need a little more room. So 1, 2, 3, 4, 5, 6, 7, 8-ish. 1, 2, 3, 4. And by pi over 2s. Usually it would look, I'll put it in blue, kind of the original version, the cosine with an amplitude of 4 would start at 4. And then dip down the 4, and then go back up to 4. But we shifted it up 4, so all these points get shifted up 4. So it'll go up to 8. This will go up to 4. This one will go up to 0. This will go up to 4. This will go up to 8. And so our new graph, I'll put in black. Look like this. Okay. And then I can finally go to my XY plane and graph it. So I'm going to make my little circles go by 2s. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, 2, 4, 6, 8. My angle lines, in this case, are at pi over 2. So 1 pi over 2, I don't really need to draw any of them. 2 pi over 2, 3 pi over 2, and then 4 pi over 2, in other words, 2 pi. So at 0, I'll put this in red. At 0, I'm at 8. And then going from 0 to pi over 2, in this first section, it'll drop down to 4. Okay, so it'll drop down to 4. And then from pi over 2 to pi, it'll drop down to 0. So it'll keep on decreasing to 0. And then from 2 pi over 2 to 3 pi over 2, it'll increase back to 4. And then from 3 pi over 2 to 2 pi, it'll increase back to 8. So you get the cardioid or snail. Okay. Okay. So you have to be able to graph these guys. I said probably give you a snail. I might give you a rose curve, either a rose curve or a snail, one or the other. Okay. Okay. Let's then go on to 10.5. 10.5 now we well, 10.4 they introduced derivatives, but in 10.5 we also introduced integrals to this new context, or this new setting rather. So let's just look at one of these. Number 15, they want to know the interior of a snail. R equals 4 plus sine theta. And again, I'll try to set it up so once you graph it, you can just use your graph to kind of answer the next question like I did on the Chapter 5 test. Okay. But this one's a little different. So let me figure this one out. First, the amplitude is 1. The period is going to go from 0 to 2 pi. And then our tick marks. You take 2 pi divided by 4, be pi over 2. And then finally, the amplitude, or sorry, there's a vertical shift. I did the amplitude for already. Vertical shift, I go up 4. That's from this number here. Okay, then I can graph that in the r theta plane or the theta r plane. I want to say r theta, but it seems like you should say theta r, right? Anyways, looks like 1, 2, 3, 4. Let's go 5. 1, 2, 3, 4. Pi over 2s. Pi over 2. Pi over 2. 4 pi over 2. And originally the sine curve would look like, put it in blue, it would look like this. Ugh. But then I have to shift all those points up 4. So go up here, next one would go here, next one would go here, and the last one would go back to the middle. Oops, what the heck did I do? Oops, the second one would go to the middle. This one goes in the middle, and then it goes down 1, and then it goes back to the middle, like that. Okay. So I just shifted all those main points up by 4. This point, this point, this point, this point, and this point. Then I can go to my xy plane and figure out what the thing looks like. So I need 5 circles. 1, 2, 3. Really? Already off to a bad start. 2, 3, 4, and then 5. What the heck? 1, 2, 3, 4, 5. And then put in the angle line, so this time it's by pi over 2s. So they're already kind of drawn for me. 2 pi over 2, 3 pi over 2, 4 pi over 2, or 2 pi. Okay, and then I'll do my drawing in red. So I start out at 1, 2, 3, 4. 1, 2, 3, 4. And I'm increasing to 5. So it's going to increase to 5 up to here. And that decreases back to 4. So right there. And then it decreases to 3. Okay. And then it increases back to 4. This is actually another snail. It's kind of like a weird flattened, like somebody took a ball and kind of smushed it in on one end. But there it is, and we traced it out going from 0 to 2 pi. So that'll be the, to get the interior of this thing, we'll need to integrate from 0 to 2 pi. And then the formula for the integral is 1/2 integral of r squared. R is 4 plus sine theta in this case. Then I have to square that d theta, and I'm integrating all the way around to get all of the interior. Okay. So I need to FOIL this. So I have 1/2 integral 16 plus 4 is 8 sine theta plus sine squared theta and d theta, 0 to 2 pi. I'm going to have to do a reduction formula on that sine squared. So I have 16 plus 8 sine theta. plus 1 minus cosine of 2 theta all over 2 theta. Whoops, this should be, the last guy should be 8 sine squared theta. Did I screw that up in my notes? No, I'm right. I'm good. I'm going insane. Okay. I'm going to rewrite the stuff so I can combine like terms. 16 plus 8 sine theta plus 1/2 minus cosine 2 theta over 2 d theta. Okay. So 1/2, 16 plus 1/2, so that's 32 halves plus 1/2, so it's 33 halves plus 8 sine theta minus cosine 2 theta over 2 d theta. Now I'm going to integrate. So I'll have 1/2 times 33 halves theta plus the integral of sine is negative cosine theta. And then the integral of cosine is sine. If you did a u sub, there would be a 1/2 constant floating about, so this would be sine of 2 theta over 2. There's already a 2 there, so it becomes 4. And then we want to evaluate from 0 to 2 pi. So this will be 1/2 times 33 halves times 2 pi minus 8. Cosine of 2 pi is 1, so it's just minus 8. Minus sine of 2 times 2 pi, sine is 4 pi, which is 0. Divided by 4 is still 0. Minus, and then plug in 0 for everything, so I get 33 halves times 0, which is 0. First one is 0. Minus 8 cosine of 0 is 1 again, so minus 8. And then minus sine of 2 times 0 is sine of 0, which is, again, 0. Okay, so I have this jazz. Let's clean it up so I can see what's going on. So 1/2, 32 thirds times 2 pi will just give me 33 pi. And then we have minus 8 plus 8. And that'll equal just 1/2 times 33 pi, which will be 33 pi over 2. Okay? Okay, so any type of problem I just did in the video is fair game for the final exam. I can do rose petals, or snails. I'll just do rose petals or snails. Were there any other types? There were just circles, I guess. So I could always, I think you can handle doing a circle as well. So pretty much anything goes. So yeah, to practice when you're on your own, if I did problem 83, look at problem 81, 85, and 10.4, etc. Make sure you can do those. And yeah, that should do it. So a lot of stuff from chapter 8. It's mainly just, do you know how to integrate? It's basically what it comes down to for a lot of it. But yeah. Okay, so hopefully that'll get you prepared for the final exam, and good luck. Okay, thanks for watching.